aside from flat or plane mirrors where we can see ourselves, which is a pretty important application of geometric optics, light traveling in a straight line, we can also look at curved mirrors. And so here I've got a circle set up, and the idea is if this is the radius, the center of a circle, that any beam that comes out along the radius, I'll send it over here, for example, because that's perpendicular to the surface, then it would just come back on itself. Okay, so that's fine. And so I'll set up another radius like this. And then we can look to say what happens for other beams of light. For example, suppose we have a little tiny laser that shines here. So it hits against that. Kind of look at a tangent. I'm going to give myself a dotted line here. And I think this would kind of come off equal angles. So if it's coming in like this, it would kind of come off like that. Sort of like that. There we go. And we could go down here, sort of having the same setup like this. And it turns out that we come back about there. Yeah, that's about split evenly. So we come back to a point right there. And that point that we come back to is what we call the focal point. Okay, so the focal point, it turns out, you can do the geometry, is just half of the radius of curvature of a spherical mirror. So if you make a mirror, so instead of making it a full circle, but you make a mirror like this, then what happens is light rays that come in basically parallel. So come in like this, like that, like this, like this. If you do your geometry, they're going to come back all to this focal point. Okay, so the focal point is the point at which parallel rays converge. That does not mean it's always the focus of a mirror. For example, if we have something that is not light that's not coming in parallel, it doesn't go to the focal point. So if we have this, if we have a section of a curved mirror, and we have this as our focal point, for example, so our radius of curvature is back over here, and we have an object, we tend to just make it an arrow object just so we know which way is up and which way is down, then we can say light rays that come off of this, because light rays go in all different directions off of this, right? Especially if it's a light bulb or something like that. So this can give us lots of light rays in lots of different directions, but we're going to focus on a couple of special rays to draw ray diagrams to see where the light's going to go and where the focus is. So the first ray I'm going to draw, so this is ray diagrams, and there are a couple that are really useful. They don't always exist, but they allow us to draw, so we can block some of them, but it still tells us where the image is. So for example, a light ray that comes in parallel will come back out through the focal point. A light ray that hits the center, I'll write all of these out in a minute, that hits the center, so it's coming out there, comes out, right, with equal angle, so it's going to come out about here. Okay, so it's going to go in and go like this. And then finally, we can have a light ray that goes through the focal point. Right? Oh, that's not very good. Goes through the focal point. Well, it looks like it came from parallel, right? Parallel rays go through the focal point. So anything that goes through the focal point comes back out parallel. And these should all cross sort of at the same point there, faking it a little bit. And this is now our image. So that's where this image is. It tells you whether it's bigger or smaller or upside down, all of those kinds of things. And we'll categorize those. But let's make sure we get our rays first. So the first ray that we've got, this first one, comes in parallel and goes through the focal point. That's the first ray. The second ray comes through the center and reflects back out at equal angles. Okay, and then the third ray, so that's the second ray right here, this greenish one. And then the third ray is this pink one. The third ray goes through the focal point and then hits the mirror and comes out parallel. And notice I started all three of the rays from the tip of the object, and so wherever the rays converge is where the image is. Notice this image is not at the focal point. The only time I get an image at a focal point is if it's something very, very far away, so all the rays are coming in parallel, so really infinitely far away, or like stars, things like that, really, really far away, they're going to have their image basically at the focal point. But things that are closer in will have their image right there. So this is a curved mirror, and these are the rays that can locate where this image is. Okay, so far we have the focal length is half of the radius of whatever circle this has been cut out of, or sphere that this has been cut out of. But we can relate the location of the object and the location of the image in relation to this focal length here. So I'll redraw this without all of the rays. So we have this, I'm going to just call object distance from here to the center. Say this is our focal length, right? This distance right here. And then in this case, we had an image that's given by that image. And what we find is that 1 over the object distance plus 1 over the image distance equals 1 over the focal length. And notice this works out if we say our object distance is infinity, then 1 over infinity gives me 0, right? So as object distance goes to infinity, then my image distance equals the focal length. So that's at least consistent. And so this is the way we can find out where things are located. If we know where an object is and know the focal length, that's where we can tell where the image is. And then the other thing we can tell, using some geometry, which I won't derive now, that your magnification, whether it's magnified or made smaller, is given by minus the image distance over the object distance. And the way to get that is you can set up some similar triangles here, and you can see that the ratio of this distance to this height is going to be related to the ratio of this distance to this height, and that's how you get the magnification. And the minus sign tells you whether it's upside down or not. And in this case, because the object distance and image distance are both positive, they're on the positive side of the mirror, if you like, then you get a magnification that's negative, which means it's upside down. Okay, just like we have here. So minus magnification just says it's upside down, and then the actual numbers you put in here tell you whether it's bigger or smaller. Okay, so we do need to say something about the sign conventions here. This is what I would call a positive mirror. The focal length is on the mirror side, right? This is black over here, or against a wall, or whatever. Light isn't coming from this side, light's coming from this side. This is the shiny side right here. Okay, so I'll make the shiny side, I don't know, a bluish color. There's our shiny side. I don't know that that shows up any better, but that's the shiny side. So when the focal point is on the shiny side, then that is a positive focal point, same for object and image. If, however, we get an image that's on this side, which is what we saw with the plane mirror, then we can have an upright image, which is kind of important. When we see ourselves in the mirror, it helps if we don't see ourselves upside down. So let's set up a situation where we get an upright image. Okay, we have another setup where I have the focal point is here. I have the object here, and I want to set up another set of ray diagrams. So I'm going to do the ray diagram, the first one, We go in parallel, and so that one's going to go through the focal point. So that's our first ray. Okay, so that's the ray that's going to be going there. So that's ray number 1. Should have made my list. Parallel to focal point. 2 is it hits the center point and comes out at the same angle, like that. Okay, so 2 is center and equal angles. Equal angles. Okay, and then the last one was the one that comes from the focal point. This one is a little hard to draw because it actually has to hit here and then go through there. So it's like light that has come from here to hit this, and then I got to hit the mirror somewhere up in here, and then it comes out parallel. So this is a mess on my diagram. Okay, so that's the setup for that. That's what's going on. And if we think about trying to collect all of these rays, this green one up here, this blue one that's coming down here, and this orange one that's coming here, we would put our eye right at this side and look back. And as we're trying to collect all of these rays, from our eye's point of view, these rays converge back here. Okay, they converge on the back side of the mirror. And so I have to draw these dotted lines like we saw before with our, maybe going off screen, like we saw before with our plane mirror, right? So somewhere over here, that's where those rays converge, basically off screen. And so I'll just cheat it in just a little bit. Yeah, you can still see that. And that's the tip of the arrow. So all of a sudden I have a much bigger image, okay? But the image location is on the minus side. So this is our image distance, and it really should be much further back to be that much bigger. This is our object distance here, and this is our focal length, right? So if we look at our equation, 1 over objects plus 1 over image is equal to 1 over the focal length. To get an image distance that's negative, notice we need this to be, the denominator to be smaller. This is going to come to this side. I can rewrite this equation. 1 over image is equal to 1 over focal length minus 1 over object. So for this to be a negative value, I need this to be bigger than the focal length, 1 over the focal length, which means I need the denominator here to be a smaller value, right? Because something smaller down here makes a bigger term up here. So that's what we get there. That gives us a negative value. Notice that when we have a negative value right here, then the 2 negatives gives me a positive, and I suddenly have a positive image. And this becomes actually a bigger number than this. So it's a positive big image. Finally, we can have a mirror with a negative focal length. That is a convex mirror. So this is convex as opposed to our concave mirror over there. And in that case, this is a diverging, if you like, mirror, because things that are coming in, let's do this parallel ray that comes in, it's not going to come back towards the middle here, and that's not very parallel, but what it's going to do is it's going to look like it came from the focal point. So it comes off like that. So that's ray number 1, coming in parallel and from the focal point. Okay, ray number 2 is fairly easy to still draw. It does exactly the same thing, equal angles. It doesn't matter the type of mirror. And already we can see that if we're collecting these 2 rays from our eye, they're going to collect somewhere in the back. And the hardest ray here to draw is this one that looks like it's coming from the focal point. Remember, we did from here to the focal point. So it's on this line. That's where it came from. Okay, and then that goes out. So from the focal point, it must go out parallel. So that's how it's coming out. So these 3 rays are the ones your eyes are collecting. And so we send this one back. We send this one back, and we sort of cheat so they all get together, and there is my image. So in this case, when I have a negative focal length, notice I have a negative number here, I subtract again a 1 over a negative number, then this image is always going to be a negative number. So the image is going to be back over here. Your image distance is going to be negative. You're always going to have an upright image. Okay, and so those are how you calculate all of those things. Now there's one other thing that we need to know in terms of describing this. So we would describe this as upright, right, smaller, and then we would call this a virtual image. And it's virtual because of the dotted lines. The light is not actually back here. Your eye sees these lines from over here and says, oh, it must have come from back there. But if we put something back here, like if I put a card or something to catch the light, it's not here. But if I do this, right, my light ray is going like this, the light is actually landing here, okay? And if I put a card right here, I would catch this, and I can catch this image, just as we do when we project things, right? When we project things, we want the light to actually be there. And so we're looking at a real, what's called a real image. So this example right here is a real image. If it's a real image, it's going to be inverted or upside down. So we always have real and inverted, or upright and virtual. You can have either smaller or larger. Same thing over here. You can have either smaller or larger. The magnification will vary some, but you'll either get a combination of real and inverted, or upright and virtual. And so you probably know this, when movie theaters had film strips, right, then oftentimes you would see that things where the film was going in upside down, because to get the real image, and it's not done with a mirror, it's done with a lens, it's going to be inverted. And of course you don't want to set it up inverted for the viewers. And there are other ways to address this. You can use a combination of mirrors and lenses to get your real image then upright, and that's what happens with those old style overhead projectors. And then our data projectors that we use in the classrooms have a combination of lenses and mirrors, basically prism setup, to get the light to the screen along with the lens so that everything is upright. But a lot of that is handled, of course, digitally, because the computer can send it out in an upside down and oriented fashion very easily.